So thank you for staying with me for the very last talk of the day. It's going to be a very theoretical talk. So I'm going to close my eyes, and those of you who want to regretting staying for this talk can do that. Okay, this was a joke. But anyhow, I'm going to speak a very theoretical result, yet very significant in the theory of multiparty computation. And specifically, I'm going to speak about optimal fair coin flipping, and this is a joint work with my student, Eliad Sfadia. Okay. So I'm going to focus on coin flipping protocols, okay? I try to give some motivation. Probably most of you won't buy it, but really it's a very fundamental primitive in cryptography and in multiparty computation in particular. So what is the coin flipping protocol? Say I and Or want to decide which movie we are going to go tonight, but I'm in Tel Aviv and Or is in Haifa, so we cannot do what we should have done, which is simply flip a real coin, right? So we want to do it over the internet, right? Again, I'm in Tel Aviv, Or is in Haifa, we want to flip a coin. So here's the way to do that. Or flips a coin and say, hey, unfortunately, it's the movie I'd like to see, okay? And I can believe it, can believe him, or disbelieve him. But this is a solution, right? It's a valid solution for flipping a coin over the internet, over the phone, right? Or flips the coin and sends the result over to me. The problem is that I don't want to say anything bad about Or, but maybe it's going to be somewhat biased, right? Because he wants to go to action movie, so he said, okay, the coin turned out to be that we are going to action movie. So can we do anything better than that? Yes, we can. Okay, in this case, yes, we can. And it was the solution given by Blum in '82. And it is very, very simple. Rather, so it goes as follows. Or flips a coin, and it doesn't send it to me in the clear, rather it commits to this coin. If those of you don't know what commitment is, you put it inside a box and send it over to me, the box, without the key. Then I'm flipping a coin as well, and sending the coin back to Or. Okay? Now Or sends me the key to the box, decommits the value, and we both set the output of the coin with the XOR of these bits. Okay? Again, Or commits to a value. I send my value in the clear. He reveals this value, and we set to the XOR of these bits. Okay? And it's not hard to see that this protocol has negligible bias. Neither I nor Or can bias the output of the coin, okay? Unless we manage to break the commitment, namely, Or managed to open the box to two different values, or I managed to look inside the box even though I didn't get the key yet, but we assume it's impossible. Clearly, in real life, no one sends box over the internet. Rather, you commit using some, say, think about it, as encryption scheme, okay? Good. So this seems like we have a solution, but it turns out not really so. The problem is, what happens, think that Or at this point knows what the output of the coin is going to be, right? He knows what A is, and he knows what B. Where I know what B is, but I don't know what A is because he didn't decommit the value yet, right? So there's a difference between me and Or at this point. So Or sees it's going to be a romantic movie, like I want to see. So, oh, my computer has crashed. I cannot open the commitment. Let's do it again, okay? So we do it again, and his computer crashes again and again and again. Still, he gets the action movie we want to see and say, okay, now this time my computer works well, and we go to a romantic movie, okay? So in setting where the honest party is allowed to abort when you find the cheats, then everything works well. But in many settings, the honest party should decide on some bit, even if the other party disappears or found cheating. This is actually, in many settings, more common than the other settings. And in these settings, there is an attack in this protocol. So why is this protocol insecure in case each party has the output a bit? Anyone can see it? Okay. If I assume that B has the output a bit, even if A aborts, say. So I say that in this case, there is an attack for A. What A can do. So with lots of generality, the only thing that B can do if A aborts, if A refuses to open the box, is to flip a coin by itself, right? Flip a uniform coin. Okay, so now O sees it's going to be a romantic movie. He doesn't like to be a romantic movie, so he says that he aborts, his computer is crashed. B, which is me, I flip now a fresh coin, and probability 1/2, it's going to be an action movie. Namely, if you do the calculation, you get a probability 3/4 is going to be an action movie, and probability 1/4 is going to be a romantic movie, which is unfair, right? I mean, simply by exploiting the fact that I have to flip a coin. I want to go to a movie tonight, regardless if O is coming or not. O can mount an attack, causing me to go to an action movie in probability 3/4. Okay. So this is bad. Let me be more formal. What is two-party coin flipping protocol? So two-party coin flipping protocol is a two-party protocol, where if both are honest, the outcome of the protocol both output the same uniform bit. Where if the adversary is trying to cheat, still I'm not going to output, my output is going to be very, very close to uniform, okay? Even if or cheats and I continue by myself, or if aborts I continue by myself, then still my output is very, very close to uniform. How close? Delta close to uniform. This is delta bias coin flipping 1 second. If you cannot bias my output with advantage more than delta, okay? And again, the honest party must output a bit even if the other party cheats or aborts or whatever. Yes?
Why not output the original bit that you flipped coin before? Why do you need to flip it?
From the same, it's even going to be worse, right? Because the original bit, now Alice, which means Oz, see what this bit is. So if he likes this bit, he's going to abort. If he doesn't like the bit, he's not going to abort. This is going to be even yeah, probably more devastated attack than the other one. Probably 7/8, okay? Because he sees, A sees in this point what's B, so you can decide between getting B and deciding A, X, or B. He has two options. Okay, both of them are uniform independent in a sense, so we can choose between two options. Okay, so again, you're going to be biased 3/4. You're going to get a action movie probably 3/4. There's no simple solution here. Okay, no simple solution. So this is a two-party coin flipping, and it was shown by Cliff back in '86 that you cannot give, unlike in the case setting where the honest party can abort if the other party cheats. In this setting, when the honest party mouse out of the bit, there's no optimal solution. And for every protocol, one of the parties, at least one of the party, can bias the outcome by 1 over the number of rounds. In our case, we have 2 rounds, we have two rounds, so you can bias the output by 1 over 4. Okay, there's a constant there that I omitted. Okay, in two round coin flipping protocol cannot be even close to optimal. It should have a constant bias. It was shown by Cliff back in '86. Okay. Therefore, we call, if one gives a protocol that reaches this bias, we call it optimally fair coin flipping protocol. If it reaches that 1 over number of round bias, not larger than that. Okay, this is the goal when trying to design such protocol. And the reason is that, I'm not going to get into the detail, but essentially if we run a protocol, one of us is going to understand what the output is before the other, okay? Think that when we begin, no one knows nothing about the final output, and in the end, both of us know what the final output is, so, one of them understands it before the other one, and therefore it can bias. Good. What is the many-party version of it? It's the same, but rather than two parties, we have many parties, and still the honest parties have to output the honest bits, the same close to uniform bits. Again, even if we have 5 parties, 3 of them are adversaries, still the honest parties should output the same bit, and it should be close to uniform. And getting such, it turns out that while two-party protocol was a very challenging task, going beyond two-party protocol, even to three-party protocol, is way more challenging task, and this is going to be the focus of this talk. Okay, what do we know? So the protocol we've seen by Blum, it gets you 1/4 bias coin flipping. Okay, the very simple protocol we've seen, the 2-round. Cleave show how to get a 1/√m bias. Okay, it's not 1/m, where every m is the round complexity of the protocol. It's not optimal. It's 1/√m. Okay. This was done by Cleave, and both results assume one function. Those of you who don't know what one function is, those results assume that you have this commitment primitive. Okay, you have this. You can send this box over the internet. Okay, it was open for a very long time whether we can do better than that, because the lower bound was 1 over the number of round, and the upper bound was 1/√of the number of round. It was open for 20 years, I think. And then in the breakthrough result, Moran, Naor, and Segev in 2009 gave optimal two-party protocol, coin flipping protocol. Optimal again, the bias is only 1 over the number of rounds. Okay, this was in 2009. There was also some protocol for many many parties, but they only hold in the cases the number of adversaries in the parties is smaller, strictly smaller than 2/3. Okay, there was no general solution. Even for 3 parties, there was no protocol, assuming that 2 of the parties cheats or try to bias the output of the protocol. And this result, unlike the result that I mentioned before, these 2 results assume much more stronger machinery than one function. We assume oblivious transfer. I guess, Tal, that you mentioned what oblivious transfer is, or no? But we assume some every machinery that allows some secure computation, but in order to exist under many, many assumptions. Okay, physical assumption and computational assumption. But still, even for 3-party case, we didn't have a solution. The only solution we had is the original due to Cleave, which achieves 1/√of number of rounds, which is not the optimal, what we think is optimal, within 1 over the number of rounds bias. Okay, so this is the game. Okay, the game for this talk, we want to give an optimally fair coin flipping protocol. We know how to achieve 1/√of number of rounds. This was known for 30 years. We want to go to 1 over the number of rounds. Why do you want to do that? Because it's a challenging question, right? I mean, why do you want to solve questions? It's a challenging question, open for a long time. Smart people try to solve it. I mean, what do we need more? I mean, unless you're in the academia, right? I mean, probably in the industry you have different different set of incentives. But yes. Good. So, is the question clear? What we're trying to do? Anyone? Okay. Let's mention negative results. So, as I said, you cannot go better than 1 over number of rounds. It's the best you can get. One party can bias by 1 over number of rounds. Whatever you assume. Quantum, whatever, yeah, I guess also quantum. Yeah, quantum definitely, but whatever you assume, you cannot do better than that. In a natural model, where crypto does not exist, but very natural model, 1/√of the number of rounds is actually optimal. So in a model, let's skip it. But in a natural model, this is the optimal. And let me skip this result as well. So what is our result? Assuming that oblivious transfer exists, we give an almost optimal 3-party coin tossing protocol. The almost comes from the fact that we have this log square m there. Okay, it's not O1 over m, but rather O of log square m over m. So there's room for more papers, I guess. To do that, we first gave a new 2-party protocol. So for those who are familiar with the literature, all the recent results I mentioned by Baimel et al. And by Moran et al. Follow a quite recent paradigm which is called the threshold round, which used to achieve fair multi-party computation. We take a very different route to achieve this 2-party protocol. And then we harness this two-party protocol to get an almost optimal 3-party protocol. Okay? This before I continue, just say why optimally fair coin flipping protocol. Okay, maybe I should say it before that, but let me say it again. So why? As I said, first, because it's fundamental natural primitive. Okay. And second, because fair computation is very important. Objective. It's very important primitive for secure multi-party computations and for many real life tasks. Okay. And while it's not immediate that optimally fair coin flipping protocol implies optimally fair general secure function evaluation and multi-party computation, it seems to be related. And it's work in progress. We're really trying to harness our results for coin flipping protocol to get general result about multi-party computation. Yes?
To make sure the three-party protocol means that all the coins are stored together?
No, given general protocol, do whatever you like. But there are three of us. Two might be cheaters, okay? And still, it should be the case that I'm going to output close to uniform bit. We're over the internet. Each of us is in a different city, and we interact in some protocol. And the result should be a uniform bit. And even if you and you cheat, still I'm going to output uniform bits.
But the method is just like with the two-party?
I can use whatever method I like. No, I can use whatever method I like. I'm free. I'm trying to give a positive result. I mean, the example that I gave is just examples. Okay. Actually, the actual protocol to achieve optimally fair coin flipping are more subtle than the example I showed. Okay. Okay. So this is the game. To start, I start with describing the cleave protocol. Actually, our protocol is based on the cleave protocol, which is a very simple protocol, very similar to the Blum protocol I already introduced. And then I show why it's not, I explain why it is not optimally fair coin flipping protocol. Hope you get some insight about this creature, which is a fair coin flipping protocol. And then I explain our solution, which fixes the issues that prevent cleave protocol to be optimally fair to get this optimally fair creature. But let's start with the basics, which is cleave protocol. So cleave protocol is simply repeating the Blum protocol for flipping one coin many times. Namely, rather than flipping one coin, we flip sequentially. We flip using Blum protocol. We flip one coin, and then a second coin, and a third coin, etc., etc., etc. And then eventually, we take the majority of this coin. The majority of this coin. Rather than speak about majority, about coins, it's more convenient to speak about -1 coins, and then I simply take the sign. I sum them, take the sign. If it's like the coin might be either 1 or -1, and if the sum is both is positive, so our final output is 1. If the sum of the coin is negative, then our final output is 0. Okay. Again, we flip m coins in m rounds. Each coin is either 1 or -1. And in the end, each of us separately sum together all these coins. And if it's positive, both of us output 1. If it's negative or 0, both of us output 0. Okay, this is the protocol. Okay, very, very simple cryptographic protocol one can imagine. Okay. Hmm? We want to output close to uniform bits, okay? So we flip, yes, it's not majority, it's not parity, right? It's whether we flip more ones or more -1s, okay? Okay, so this is the output. What happens in one of the party aborts? So, it's m rounds protocol. Every time we flip in each round, sequentially, we flip one coin. About in one of the sum round, in the sampling of one of the coin. What the other party does in this case, it resamples all the remaining coins and output the sign, whether it's positive or negative. Okay? So effectively, by aborting, what's the effect of aborting? Again, know that in each of the sub-round, A get to know the final output of this round coin before B does, right? So what the effect of aborting? I mean, what Alice can do? Alice, the only thing she can abort. She cannot open the commitment to 2 different values. So she can abort, okay? Actually, it turned out to be the most devastated attack a cryptographer can do is aborting, okay? So Alice in the first round, she wants to get the final output going to be 0. She noticed that it's going to be 1 because she knows she committed to A1. She got B1 from Bob. She knows that A1 times B1 is 1. So, oh, I want it to be 0. So what can she do? She can abort. What Bob does in this case, he's going to resample the first coin and on the remaining coin. So effectively, by aborting, which is only effective attack Alice can do, she makes the other party to resample one of the coins. Not all the coins, but only to resample one of the coins. The previous coin was already set, and the future coins were not sampled yet. So she makes the other party to resample one of the coins. This is a very effective attack, but not too effective. Not too effective because one coin does not affect the final sum too much. How much does it affect it? But 1 over the square root of the number of coins, which I'm going to prove. Okay? This is the core of the issue. Okay? Essentially, because if you want to think about it differently, because we're not designing the final output at once, it's like a gradual shift from the final. In the beginning, the expected outcome is 1/2, and then in the end, it either goes to 1 or goes to 0. Because the shift very slowly, by aborting, you don't change it too much. Okay? Okay? Is it clear? The protocol is clear? Not the analysis, but the protocol at least is clear? Good. So as I claim, this is 1 over square root of bias protocol. I'm going to prove it to you. I'm not going to give the simplest proof because I want to then to reuse this proof for analyze our protocol. There's much more simpler proof, but I'm going to give this proof, which is somewhat more complicated. Yes?
Is the assumption in all this that Alice aborts every time she doesn't like the answer?
She can abort once.
She can?
Yeah, only once. You know, you cannot say that.
But isn't it always better for her if she aborts every time she doesn't like the answer? Or?
It depends, you know, like now we want to analyze what is the best strategy for Alice for aborting. But I said she can abort only once, okay? You cannot say that, yeah, after your computer has crashed, it has crashed, right? I mean, you cannot say it crashed again, you know? It's already dead, right? So a party can abort at least once, at most once.
Only once?
Only once. She can decide whatever she likes to abort or not to abort at all, but she can abort only one. It's not how to show that her best strategy to abort is to wait. She wants to get 0, to wait till the first coin turns to be 1, and then she aborts. This is the best strategy for her, okay, without getting into details. Yes?
But if she waits until the last round,
yes,
and she knows definitely that she's going to lose,
yes,
and then she aborts.
But then she gains nothing. It's a very good question. Because if in the last round, if some Ci I equal 1 till a minus 1, say, assume this is 7, okay? And then the last coin is 1, and she aborts. What Bob does, it only resample Cm. Okay, so it's going to be minus 1, so the final outcome, rather than being 7, is going to be 5 or 6. It's still going to output 1. She's not going to affect the output at all. She's only going to affect it if you wait for the last round, if the sum here is exactly 0. But the probability that the sum of the first n minus 1 is 0 is small. How small? 1 over the square root of number of rounds. Okay? How much time do I have? Or I forgot to start the time. 30 minutes. Good. Good. So how do we analyze this protocol? So first, you can assume without generality that the only, I mentioned it before, that the only attack that Alice mounts is aborting. As I said, we are very good in crypto to prevent you from cheating. Okay? You can prove that you're not cheating, etc., etc. There are different techniques. But there's one thing we cannot prevent you from doing, is to die. Okay? If you die, you abort, you disappear. There's no way to prevent that, okay? Because there's no way to prevent it. This is the only possible attack, and it's very effective, actually. This is what exactly prevents you from getting a perfect coin flipping protocol. So we assume that. So as I said before, what does Alice get from aborting? She gets the difference. So she's in this, assume that is in this round, say after the first round. She knows what the value of the first coin is because she's the one that committed to the box, and Bob doesn't. Alice didn't decommit the first coin. So what she gets is she knows after she saw it's going to be 1. So she knows what is the expected output of the protocol given the first round coin, where Bob doesn't. You only know what the expected output of the protocol when it starts with 1/2. Okay? So this is an advantage. The difference between the value of the protocol from her point of view, when she has more information, versus the expected output of the protocol from Bob's point of view, when he has less information. If the difference go to her direction, she's not going to abort. If the difference is going to be to the other direction, she might abort if she like. So this is exactly what you gain. By aborting, Alice gains exactly the difference between the expected output of the protocol from her point of view versus the expected output of the protocol from Bob's point of view. Okay? This is the only gain she gets from aborting. Okay? If this difference is large, like in Blum protocol, which is a constant, it's too bad. If this difference is small, we are in a good situation. Okay? I'm going to show you that in this protocol, in Cliff protocol, the difference is 1/square root of number of rounds. Okay? Good. What happened to my clicker? Good. So let Sk, sorry for that's a very little of math. Let Sk be the sum of the first k coins. Remember, it's a -1 coins. Each of them is uniform. Okay? And excuse the mathematician among us, let's assume it's uniform over the interval -square root of k plus square root of k. Okay? It's converges close to the uniform to the normal distribution just for the sake of this talk. Okay? Okay, good. So assume that after the first I round, after the first I round, or the sum of the first I coins is very far from 0, is larger than square root of m minus I. So if this is the case, the value of the output of the protocol is already set. Where is that? Because we only have m minus I coins to go. With I probability, as I said, or under a simplified assumption, is going to be uniform in -square root of m minus I plus square root of I minus I. And if I'm outside of the region, then the output of this protocol is set already. So by aborting, Alice gets nothing. Okay? From to the extreme, if in the very last round the sum is 7, Alice gets nothing by aborting. The output is going to be 1 if she aborts, or if she decides not to abort. So only the game only in this region. And if we are in this region, if the sum of the first I round is smaller than that, by aborting, she gets 1/square root of number of coins, 1/square root of m minus I. Why is that? Because she's only going to get by aborting if the output of the coin without aborting is exactly 0. And again, because there's m minus I coins to go, and they're uniform over the interval of order square root of m minus I, is up in the probability 1/square root of m minus I. If you do, and what is the probability? Finally, what is the probability that after I round is going to be an effective region? The size of the effective region over the probability over the size where it's going to be uniform over, which is square root of m. For those who didn't make the calculation, exactly, it follows that the probability that in the ith round she's going to be, if you multiply the probability that after the ith round she's going to have she's in the effective region, she can attack, and the probability if she attacks divides the output gets to be, you do the calculation, gets to be 1/square root of m. Okay, for those who didn't follow, it's not that it's important, but not that important for the rest of this talk. Okay? But it all comes up from the fact that if you look at the sum of m coins, they're uniform. The only mathematical assumption you assume are uniform in a region of square root of number of coins, more or less. Good. So this is the Cleves protocol. Okay. And as I mentioned, what prevented Cleves protocol from being optimal? What prevented is that there's a difference of exactly 1 square root of m between the output of the expected outcome from Alice's point of view and the expected outcome from Bob's point of view. And this happens actually even after the very first round. After the first round, if the first coin is 1, then the expected output of the protocol is 1/2 plus 1 over square root of m. Let me write it down. If C1 equal 1, then the expected outcome is 1/2 plus 1 over square root of m. Okay? This is after the first round. So this is from Alice's point of view. And from Bob, because he doesn't know what C1 is, the expected outcome is simply 1/2. Okay? Because no coins were flipped yet, and this is the uniform, the output is the uniform bit. So even after the first round, Alice can achieve this bias simply by waiting for the first round. If it's 1, she aborts. If 0, she continues not aborting at all, still she gets 1 over square root of m. She biases the protocol by 1 over square root of m. So not only this protocol is not optimal, it's even in the very first round. But again, the reason is that there's a gap between what Alice thinks, even after the first round, what Alice knows about the expected output of the protocol versus what Bob knows. So how can you fix it? And then Bob can cheat. Whatever you do, you can prove that actually. Whatever you do using this machinery, one of the party can cheat. Okay? But what can you do?
Do we have to have the one that the commit is only one way?
No, you can commit both directions.
So does that help?
No. But let's assume that someone can give Bob, before the very first round, what's going to be the expected output of the protocol after the first round. Okay, this is going to be very bad. But then Bob can attack, right? If Bob going to be the expected outcome going to be 1 over square root of m, he can attack. Rather, don't give him the value, give him a sample from the value. Again, if the expected outcome is going to be 1 over square root of m, give him a sample, a bit, that is 1 with probability 1 over square root of m, and 0 otherwise. Okay, again, I'm not going to give Bob what is the expected output of protocol after the first round, because then he can attack. Rather, only give him a sample from this distribution. I'm going to give him 1 probability 1 over square root of m. As the difference is perfect, it totally prevents Alice from attacking. Because if Alice aborts, she knows that Bob is going to output a sample from the expected output of game given the first coin. So there's no difference between the expected output of Bob and the expected output of game as Alice sees it. So she gains nothing. But still, now, even though Bob didn't get the expected output of the protocol, he still gets a hint about the expected output of the protocol. What is this hint? This sample. But this sample is a very noisy information about the expected output of the protocol. It can get 0 even though the expected output of the protocol after the first round is 1/2 plus 1 over square root of m, and vice versa. Okay? So if we are able to give Bob this sample from the expected output of the protocol after the first round and to give it to him before the first round, we are in good shape. We are in good shape because Alice cannot attack at all, and Bob can attack, but because he got some information, but it's much less information than in the original protocol. He didn't get exactly the expected output of protocol, which jumps about 1 over square root of m. He only gets a sample from this value. Yes?
So we assume that both parties can cheat.
Always. Always can. If I assume that only one party can cheat, I can give you to flip the coin. Both parties can cheat.
So what prevents Bob to just output whatever he wants?
No. When Bob cheats, he can output. But the goal, when Bob cheats, his goal is to make Alice output a far from uniform bit. Okay? When you cheat, you're trying to make me, to bias me. When I cheat, I try to bias you. Okay? It's clear that if you want to bias yourself, I cannot prove it. But when Bob cheats, you want to bias Alice. Okay? And so in this solution, again, indeed, Bob will be able to cheat, but he won't cheat as much as Alice could, because he knows less about the expected outcome of the protocol. Let me put it more formally. Okay. So before that, but how I said, like, assume that Bob gets a sample from the expected outcome of the protocol after the first round, before the first round. Who's going to give him this sample? I mean, if Alice gives you the sample, we are in very bad shape, because Alice knows exactly what Bob is going to output the case of a board. You know, bias the protocol by a constant. He cannot, on the other hand, he cannot sample it because he does not know what is expected after the protocol after the first round. He didn't get the first round coin yet. So who is going to sample this value? Any solution? We can ask for fair parties to sample this value. I mean, but if we're a fair party, maybe he can flip the coin for us. Okay? So we cannot assume fair party. What can you do? So the idea is to use non-fair secure computation to sample this value. Again, as Tal mentioned, I'm going to speak tomorrow, we have a very developed machinery of secure computation. We can compute any value, any function that you like, but in a non-fair manner. Okay? It turns out for sampling this value, we don't need fairness. It suffices to use non-fair secure computation. And it's going to do to get at what we like. So what is this? We assume we have the non-fair dealer. What do we mean by that? We assume that both parties has access to some dealer, which is honest, and he gives shares or gives value to each of the party. Okay? And then, after the dealer gives this auxiliary information for each of the party uses this information to interact in the real protocol. Okay? But I emphasize that this dealer is non-fair. Otherwise, it would be a very simple solution. The dealer would flip a coin and give us to both of us. No, the dealer is not fair. He first gives or the output and then give me. So if the output is going to be the coin, we are dead. Or after getting the coin, can say the dealer abort, and then the dealer aborts. So the dealer is non-fair. Okay? So the way we use it, the output of the dealer is going to be nonsense for each of the party. It's going to be secret sharing of some value, and each of the party, after getting the output from the dealer, know nothing. When we start interacting, then this share is going to get meaning, and then you can use it to get a protocol. This is not, I mean, it's used also in previous to get a previous fair secure function evaluation. It's a known paradigm, yes?
So do the players have to pass their information to this dealer first?
We can give information. We can, typically in our case, it's simply the dealer, simply is random, he flips some coins. He doesn't have to give me any information. We don't have to give him any information. Okay? And assuming oblivious transfer, assuming you have secure function evaluation, then if you get a delta bias coin flip protocol, then in this model, in the dealer model, in the non-fair Miller model, you can translate it, you can compile it into a delta fair coin flip protocol in the standard model. Okay? So you can develop it very convenient. You can develop, when you come to develop a protocol, you can develop it assuming this mysterious dealer, non-fair dealer, and then use oblivious transfer and you don't need it anymore. Okay? It's only abstraction. Okay? For the rest of this talk, you can assume you have this dealer is non-fair. One of the party gets his output first, but is honest. Yes?
Didn't you want to get rid of the delta bytes?
Mm-hmm.
Didn't you actually want to get rid of the delta bytes?
No, I want to get delta as small as I can. I want to get delta 1 over number of round, where we know to get 1 over square root of number of round. As I said, it's impossible to get rid of the delta. Ultimately, it's impossible. Okay? So just demonstrate this paradigm. Let's rethink about Cleave's protocol using this dealer. So what does dealer do? The dealer samples the coin by itself. Okay? He samples all coins right at the beginning, but he don't give them as is to the parties. Rather, he secret share each of them and give share for each party. What does mean secret share? Means that if flip C1, you see it? It's possible to see it? No reflection. So he flips C1. He doesn't give C1 to the party. Rather, he flip another coin. Let's call it X. Let's call it X1A. Flip it totally in uniform from, say, 0, 1. And then he set Y1A to equal C1 XOR X1A. Okay? And you give one party this value and the other party this value. It's easy to see that, since note that regardless what the value of C1 is, X1 is clearly uniform, it's chosen uniform, but also Y1 is uniform because it's a XOR of some value with a uniform bit. So none of the party learns nothing about the first coin giving the shares. So we give them, for each of them, is give the shares for all coins, but at this point, they learn nothing about the coins. They only got the share. Yes?
Does this mean the dealer is doing all the coin flipping for the whole?
Right in the beginning, before the protocol starts.
So Alice and Bob don't get to flip any coins?
No. Yeah, they don't need to flip any coin. The Alice and Bob can be deterministic. Yeah, they are deterministic. So he flips all coins, but this coin is going to be released gradually. Okay? So he flips all coins and gives all shares for both parties. Now, in each round, the parties reconstruct a new coin. Okay? In the first round, we construct the first coin. In the second round, we construct the second coin, etc., etc. It's exactly the same like the original protocol, but rather than using commitment, etc., we're using a dealer and reconstruct the coin. It's totally, you don't need such heavy machinery for getting this protocol. I just wanted to explain the dealer paradigm. Okay? 15 minutes or? Yes? Good. So this is Cleave protocol. Okay. And again, the output is the same. Each of the party output the sum of these coins. Okay? Okay. But now that we have this machinery, we can improve the dealer. How are we going to improve the dealer? The dealer, again, sample all coins right from the beginning. He knows all coins, as it should, uniform and everything. But now, you look at the first coin. You know what the expected output give you the first coin. It might be either 1/2 plus 1 over square root of m, or 1/2 minus 1 over square root of m. And now, he sampled difference value, the difference value I mentioned before, the values Bob is going to get, according to the expected outcome. He sampled the difference value. Again, after you look at the coin one by one, in each point you say what is the expected output of the protocol given the first I coins. You calculate this value, sample two difference value according to the expected outcome, namely there are one probability, say 1 plus 1 over square root of m. In the third round, there are one different probability, and secret sharing this different value again and give them to the party. Now, in the end is the execution of the dealer. In the end of the execution of the dealer, the parties not only have shares of the coins, but only have shares of this different value, which is going to instruct them what to do if the other party aborts. Okay? So who is the one that sampled this difference value? The dealer. Okay? It is true that both parties invoke the dealer, but we don't care about for now. You have some machinery that allows you to sample correlated value, okay, and to give them when you like. Okay? So the way it's actually done, that in each round, before they reconstruct the first coin, both parties reconstruct the difference value, which tells them what to do in case the other party aborts. And only then they reconstruct the first coin. Then, before reconstructing the second coin, each of the value reconstruct, so the parties help the other party to reconstruct his difference value, which tells him what to do in case the other party aborts during the second round, etc., etc. So they help each other reconstruct the difference value and then the coin, the difference value and then the coin. And now, if one of the party aborts, the other party looks what is the most recent difference value it has reconstructed and simply output it. Okay? So I'm helping you to reconstruct your difference value. You're helping me to reconstruct my difference value. Clearly, you can abort at its point. In my point, I can say, I don't want to help you reconstruct your difference value. This is an attack. But it's way less effective attack than attacking on the original protocol. Let me try to explain about that, and probably then after that I'm going to sum up. So again, this difference value, the difference value that Bob gets before the first round, is the expected output of the protocol after the first coin is reconstructed. So at this point, Alice has no point at all to reconstruct it after the first coin, because she knows, she is sure that if she is going to abort after the first coin, the expected output of Bob is going to be exactly from the right distribution. She gains nothing. So when can she abort? She can abort in this round. She waits, she is reconstructing her difference value. She didn't help yet Bob to reconstruct his difference value, and now she can abort. Okay, this is the only gain she has. She knows additional information compared to Bob. What is this additional information? It's not the coin, which would be too bad. It's only the difference value. But we constructed this difference value to be less informative about the expected output of the protocol than the coins. This is our gain. How less informative? Exactly what's going to move us from 1 over square root of m to 1 over m. So as I said, aborting in this round is harmless. Aborting in this round is effective, and it should be effective, because we cannot get optimally, not optimally, but ideal coin flipping protocol. We know that we should have some bias. This was proven in '86. But exactly give you what you should get, which is 1 over a number of rounds. And so I claim that aborting in this round is not too harmful. And the reason is that, let's jump to the point, if you're not in the effective region, as in the original protocol, you gain nothing. If you're in the effective region, so you're in the effective, the output of the protocol is not set yet, and you get a hint. Highly set advantage of Bob, she knows a difference value. But if you make the calculation, which is not too difficult, you see that the difference value does not give us too much information about the expected outcome. And therefore, you get that if you do the calculation, you get that the bias Alice can get is not 1 over m, as we like, is 1 over square root of m times m minus I. Too bad, because it's not good enough. It was good for very small I, so Alice cannot abort in the first round. She cannot get too much by aborting in the first round. But it's not hard to see that if she waits for the very last round, it's very bad. And it should be very bad, because in the very last round, the difference value and the coins are the same, right? The difference value tells you exactly where the coin is. Okay? You know if the difference value is 1, you know that the coin is 1. In the last round, you boil down, the explanation boils down to the original protocol. So what do? And again, when even the Cliff protocol, when Alice said there's effective attack, if it happens that the first m minus 1 coins the sum of them happens to be 1, which in Cliff protocol, 1 happened with probability 1 over square root of number of rounds. So we want to change it. We want to give less weight to the high order rounds and give more weight to the first round. How can you do that? Again, you want the first round going to affect the final outcome more than the last round.
Don't use majority function.
Exactly what should you do?
You shouldn't use the majority function when you decide on the output value.
Okay, but what can, okay, this is. Use a weighted majority. Exactly, this is what you do. So use weighted majority. This is one example. You can do a different one. In the first round, rather than flipping one coin, flip m coins together. Okay. In the second round, flip m minus one coin. In the third one, m minus two coin, etc., etc. In terms of this does the work. Okay. By using majority, you give less power to the last round, and then you balance everything together, and you get what you like. You get that the protocol is 1 over m. Okay. So let me go to. I'm skipping the free round protocol. So the free protocol is still some few one or two challenges to go over, but I think the conceptually the crux of our approach is this understanding that you have to give difference value to rather you have to defend the protocol, and if you use the right protocol and turn out the cleave is the right protocol to be the starting point, and you defend it, everything more or less go as you like. Okay. Okay. So let's skip the free party protocol and summarize. Sorry. I was optimistic. Okay. So let's summarize and move right away to open questions. So one important open question, at least in your, you think similar to the way I do, is to remove the log square m factor. Remember, we don't get 1 over m fair coin flipping protocol, neither in the 2 round nor the 3 round, but we pay a factor of log square of m. It turned out to be very, very challenging question. Very related, those of you know, to what's called the secretary problem. Okay, it's some problem or related to optimal halting time. Okay, it's a very difficult problem. I spent more time on removing this log square of m than on the original question, actually. But I still was not able to do that. Second one is to go more than 3 parties. So it took 21 years to go to do the 2 parties. Then it took 5 years to do 3 parties. So if you do regression, you're going to take something like 1.5 years to do 4 parties. And you're going to converge in 2 years, we're going to finish everything. But yes. So it's still, even 4 parties, very challenging. We have no clue. We have some clue, but not really. Another very interesting question, as I mentioned, for Cliff protocol, it suffices to use commitment. To get commitment, you need to use the minimal order assumption exists, which is the assumption that one function exists. Where to get optimally fair protocol, you need to use way more strong machinery, which is oblivious transfer. Okay? The question, but we don't know if it's necessary. As far as we know, you can get optimally fair coin flipping protocol only assuming one function. Okay? This is open question. We don't know its answer. It's very interesting. And the last one, as I mentioned, is can we take this machinery to get optimally fair, secure multi-party computation? Okay? Not only here we gave for a specific function, which is coin flipping or XOR, but can we get for general multi-party computation? We don't know. Oh, that's all. Thank you. is the assumption that one function exists. Where to get optimally fair protocol, you need to use way more strong machinery, which is oblivious transfer. Okay? The question, but we don't know if it's necessary. As far as we know, you can get optimally fair coin flipping protocol only assuming one function. Okay? This is an open question. We don't know its answer. It's very interesting. And the last one, as I mentioned, is can we take this machinery to get optimally fair, secure multi-party computation? Okay? Not only here we gave for a specific function, which is coin flipping or XOR, but can we get for general multi-party computation? We don't know. Oh, that's all. Thank you. Questions?